There should be some excess ones over there at the back. Please give it to the left side as well. Any excess, give it to the left side. Okay. Now, just a few remarks before we start. Next week, you're going to have a midterm. And this Friday, I am going to distribute an information sheet for the midterm. There are a number of things that I'm going to write there, but just to give you an idea, I will write about question types, which can be anything general. You have probably seen that in your homework as well. The type of questions that you are asked in the homework are the typical questions that I ask during the exam. You can have a variety of different types of questions. There is no question structure that you can study or so on. It depends on what I am thinking Tuesday night before the exam when I'm preparing the questions. Okay, so this is number one. Number two, there are a number of comments that we have distributed for, well, we have already distributed comment for quiz number one. Comments for quiz number two is going to come, I think, tomorrow with the grades. And comments about the homework is going to come an hour after you submit your homework. Okay? We are not, unfortunately, we won't be able to grade your homeworks before the exam. So there will be 3 different comment statements. Plus, there is also a long writing that I had for the term paper homework. You are responsible for reading those as well, okay? Because I may ask certain questions that I have in the comments as a question. It would be a good thing for you to work. Actually, I'm going to rewrite the study things that you can have, the study references, and I will include those comments there as well. So that's about the question. I don't know the length of the exam, and I will have no idea about the length of the exam, even at the point that we start the exam. So we will all learn about how long the exam will be when we distribute the exams. Okay? The exam is going to take place here and upstairs, and we will start as soon as everybody is settled. Last week on Wednesday, I made an experiment on basically to teach you how to settle in the classroom. Okay? Now you learned you are going to sit in this kind of a classroom. I was a little bit anxious and nervous so that you will sit and will start immediately. Moreover, I am one of the believers who thinks that if you are more under stress, under a certain level of stress before the exam, rather than being very relaxed, you will be very successful because you can concentrate more. So if I were you, I would come here a little bit early, like 5 minutes early. Make sure that you are ready to go 5 minutes before the exam starts. Okay? And I will set the starting time of the exam, not 3:40, probably 3:45. So this means that I want you to be here at 3:40 and seated in the correct way so that we don't spend any time and energy to make those things more understandable. Okay. And that's, I think, the assistants, I'm very glad to hear from my assistants that a lot of people are going and asking questions about the quizzes and other things to them, to my 2 course assistants, not the student assistants, because still you don't know them. And I'm very glad that you are using them because they are there to support your work in this class. Now, they are also going to have their office hours, regular office hours on Monday and Tuesday, so you can ask questions to them on Monday. And I think it's only on Monday. Am I right? Yeah, because I don't remember the exact times. But they will be available in their office hours next week. Now, I will only be available if you write me an email ahead of time. I have a very busy schedule next week, unfortunately. But if you tell me that you want to see for some purpose, I will make sure that I will be able to spend 15 minutes, 20 minutes with you before the exam. Now, in the period up to that exam, last week and so on, I have seen a lot of students from this classroom. So I'm always available, actually, but I don't like to be very much available before the exam. okay? Because I am sort of thinking about questions that I'm going to ask. I usually prepare a day before the exam. And so I'm very much concentrated on that. I don't want that concentration to be ruined by a certain question that I may ask you. Okay, if somebody comes and asks me a question, because you are 200 plus students and all of you are very smart, you can guess certain questions. And if you start asking me questions, then I won't be able to find questions to ask you. And another thing is I will probably supply you, I'm saying probably this is 99%, again with a text before the exam. Okay, and I will send it with an email 48 hours before the exam. And of course, you can try to guess the types of questions that I will ask from that text, but you are responsible from knowing all the words that are in that text. So we are not going to answer any questions regarding the meaning of a word from that text during the exam. Okay? Actually, another thing that I should say is my motto in general is not to answer any questions during the exam. Okay? And I will try to keep it this way, because imagine if you start asking questions in this group, nobody will be able to concentrate on the exam. So my motto in general is not to allow you to ask questions. But I usually do it this way. You go over the exam quickly in 5 minutes. If you think that you have a question, you raise your hand and I will come to you. But towards the end of the exam, probably I'm going to shut the doors and not let any questions to be asked. Okay? So if you think that there is a mistake, which is very possible, of course, you can simply write that I think there is a mistake like this. I took it this way. You make your assumption and go ahead with that. Okay? That's the way that you should work, because there will always be mistakes. There is no correct question to be asked. Okay? Any comments? Okay. Now, today we're going to work with networks. So we're going to see two different things that will probably occupy your 8-9 weeks in the coming courses, in two coming courses, in total of 8-9 weeks. So what I will do is I will give a taste of that. And just to show you that, we can, when we convert certain things to mathematical structures, we have certain ways of handling it. So we're going to see a simple example regarding that case. And this is basically routing through networks. Now, where is it? Okay. Now, my objective is not to teach you how to solve certain type of problems that you're going to see. Of course, we're going to see two types of problems. For one of them, we're going to have an algorithm which is going to solve it optimally. We will be able to find global optimal solution. We will talk about that. In the other one, it will be very difficult. We will see that we can easily solve small problems, but when the number of parameters in the problem increase, we won't be able to solve. But we're going to have some approaches to solve that problem. So we're going to learn what a heuristic is. Okay, so this is the game plan for today. So we want to become familiar with the basic elements of a network, which is a very common structure that you can model various different problems. We have already seen a number of them, but I will be more specific after this point. Let me start with a specific problem for a network. What we want to do is we want to find out the shortest route for a delivery truck. Think about how many of you are familiar with Atatürk Orman Çiftliği? This is one of the milk. I think they usually have milk and ayran, and it is local because it is grown. They are manufactured in Ankara, but it's very old. It's probably like 100 years old. Now, think about this factory in Ankara. Most of you know it. I can see that. So we have this local factory in Ankara, and this milk is consumed in almost all large supermarkets, plus in very small bakkals or grocery stores as well. So But we're talking about not a very big operation. It's relatively a small operation. So this milk truck leaves, and there are certain destinations of the milk truck to go. So, for example, we're going to start with going to a certain shop. And what we want is, among all possible routes, we want to make sure that we will reach this shop in the closest possible way. Now, what do we mean by closest possible way? It can mean two things. We might want to minimize the total distance to go there, or we might want to minimize total time. Now, time and distance, you would say, are usually related. However, we're talking about a big city. You don't want to go into a huge traffic of aydınlık evler or something like that. So you want to make sure that your time is important for you. Regardless whether it is time or distance that we use as performance measure, this is the problem that we want to solve. I want to go from A to B. There are two nodes, from node A or from point A to point B, and there are possible alternatives to go there. I want to make sure that I reach there in the easiest possible way. Okay? So any doubts about the problem? Now, if you read the PDF in the website, there are numerous examples given there, a number of cases. And so please do read that, because they will give you a lot of motivation, plus understanding of the type of problems that you can solve with this approach, or with this specific problem that we will talk about. Now, basically what we do is, this is something that we do every day. So if you are going to go from one point to the next, maybe you are not going to think about, let me find the shortest distance, or let me find the minimum time route. What you would do is you would casually go from one way. You don't care. But what happens if you do it every day for 60 years? Okay, now that becomes important, because every minute that you are going to save is going to be counting for something. Or every distance that you don't go is going to decrease your cost. So this is a repetitive operation. Now, example one. Some of you are staying at the dorm. I'm sure that you already have ordered something from Sözeri Kebab. Okay, how many did order from Sözeri Kebab to their dorm? Considerable, 25. In 3 months' time, this number will be 50. Because at the time of your finals, you will order more frequently. I remember my daughter ordering Adana at 10 in the morning. Okay, and the guy said, well, what are you going to do, Adana, at 10 in the morning? She said, I'm confused, because I have been working all night. So that's the story. So you're going to learn that. Now, question here is, you are going to deliver to different dorms. And Sözeri is doing this continuously. Okay, so you call from dorm 71, you call from dorm 51, you call from dorm 36. I don't know whether they exist or not. Okay, but these are the dorms. So they know how to go there, actually, in the best possible way. Those motorcycle guys, or sometimes they walk, but they always take the shortest route. So this is something that they do. It would be very good if Sözeri had a map in front of the guys who are making the delivery guys, and they are going to select the route that they are going to reach to certain places. Now, the objective is not to go from the shortest route only. Think about the PDEs that they are carrying. It should be warm when you receive them. Okay, that's the key. Okay, so this is number one. Number two, mail delivery. Think about a mail person who is delivering mail to your apartment or wherever you live. And that is a repetitive operation. It's done every day. Okay? The problem is a little bit different, of course. You're not trying to reach from one point to the next, but you are trying to make sure that you go to all the apartments on the street, on one street, and then go to another street. Okay? So it is a different type of a problem. We're going to talk about that as well. The third one is goods delivery for a retailer. Okay, think about Amazon.com or think about Amazon.com. Yeah, I think it's a good example. Amazon.com is sending certain things to different locations. Now, this problem is so big for Amazon.com that they don't do it themselves. What they would do is they would actually subcontract that to other delivery systems like Federal Express, USP, United Parcel Service, or so on and so forth. So they actually don't do it themselves. But if you are a retailer, like Gima, for example, not Gima doesn't exist anymore, but Migros has a home delivery system. When you buy certain things online, they are going to deliver it to your place. Now, again, they have to solve this type of a problem. Now, another example is electricity meter reading people. What they do is they read the meters throughout the streets. They are like the mail delivery people. Okay? They don't do it every day, of course, but they do it in a certain frequency. Now, you can see that I can increase these examples. One of the newest examples is that you have space stations. Okay, this is a real project, by the way. You have different space stations. So you are going to deliver certain goods which are necessary for space stations. Now, in which order are you going to do it? So to solve this problem in a three-dimensional medium is rather different than solving it in a two-dimensional medium where you are restricted with roads. There you are restricted with other things. So it's an interesting problem. It's one of the projects that was taken, I think, if I'm not mistaken, 4 years ago. So you have certain things to deliver, and how are you going to do that in the space? Okay. Any problem with respect to motivation? Okay, we are all motivated to find out how we can solve this problem. Now, let's give some names. Let's give some names which are, I think, very important to put on. After giving some names, creating a jargon, we can easily communicate between us the type of problems that we want to solve. Now, I think it's not very, well, maybe I'm too close to that. Let me see. No, I think there is something wrong with the figure probably. How about yours? Is that clear in front of you? No, okay. Okay, but you can guess what's going on. So what we have is we have 6 nodes here. Okay, these are called nodes. And the lines that connect nodes are called arcs or edges. So a graphical representation with nodes and arcs or vertices and edges, you can use all these words, and you're going to learn whether they are a little bit different than each other. But basically, the idea is that we represent certain geographic location with nodes, and with arcs, we represent the connections between those geographic locations. Now, you can guess, for example, this might be a street map, where each node may represent a certain junction. Okay? So this is one road from here to here, another road from here to here, another road from here to here. This is a physical interpretation of the network. However, these arcs may be a combination of different routes that we come up with. For example, if you are carrying with a truck, there are only certain roads that you are allowed to take. So if that's the case, then there might be other junctions here that you are not going to represent because it's not going to make sense for your problem. Okay? So basically, what we call these nodes, whatever they represent, and they connect the arcs as the lines that connect those nodes. Usually, we draw straight lines between nodes, but if we don't draw straight lines, it doesn't necessarily mean anything special. Okay? Sometimes, in order these arcs not to intersect, okay, what we do is we draw nonlinear arcs. so that they are not going to intersect. It doesn't mean anything. It's the same thing. The distances that we have in between nodes are not necessarily represented with scale in these type of graphs. In these type of graphs, networks, what we represent is the relation. Here you can see that we don't have a direct connection between these two nodes. We only have direct connection between this node, and the other two are these nodes. Okay? So this is basically what we represent here. Now, of course, you can say that this might represent a physical process that we have been talking about. That might be a possibility as well. Yes, you're right. It may represent that as well. So regardless of what it represents, we are going to solve a problem in the first part of this week's course, in which we would like to go from one node to another in the shortest possible way. But we have to define certain other things to do that. Any questions up to this point? Any questions? Anything that is not clear? Okay, let's move to the next slide. Now, we represent real processes by networks. And in those cases, usually nodes would represent geographic points like cities, intersections, railroad stops, production points. Now, we might represent each node as a production point as well. Think about the what was the example that we had? The airport example. Okay, we had nodes there. You can assume that each of them you are doing something, it's a production point, and you are going to the next one. So we can represent it with nodes. But it can well represent a city. So we are talking about bus travel in between cities. Or it can represent railroad stops. So you are talking about visits to different cities by using railroad. Okay. Now, arcs often represent links between nodes, so it is going to be roads, railroad, or it can be the path that you use in between two operations. It can be a road as well, of course. Okay. Now, arcs can be undirected, which means that you can go from one node to the next, or you can come back from the next one to the previous node, or we call it two-way, or it can be directed one-way graph, one-way arc. What is the meaning of one-way arc? You can only go in one direction. Now, let's give an example. Well, the streets. If you have a one-way street, then you can only go to this direction. In case of production, usually you have one-way arcs. Because you finish this operation, then you finish the next operation, and then next operation, and so on and so forth. Okay. Now, these are all things that you can represent in real life. Now, nodes, arcs can be uncapacitated or capacitated. Now, what do we mean by capacitated? It means that if we're talking about, let's say, an arc, it's a certain road, or it is a pipeline. You know what a pipeline is? The pipeline that we are carrying oil from Iraq, or there is another pipeline that we are carrying natural gas from somewhere in the north. Okay? So pipeline is capacitated. In other words, per second, the amount of oil that can flow through that pipeline is probably proportional to the diameter. So in that case, it's a capacitated arc. If we're talking about a road, it's again a capacitated arc. In general, actually, all the arcs are capacitated, but for different problem environments, we don't consider that as important. Your kebab delivery problem, it's capacitated, but how many kebabs are you going to deliver so that that road in between Sözeri and your dorm is going to be crowded with kebab carriers? Okay, that's difficult. Okay. Well, you never know, of course. Okay. And similarly, nodes can be capacitated. What's the meaning of that? Maybe the number of times that you can visit a certain node may have an upper bound. For example, at some points, at some specific time durations during the day, you're not allowed to go to certain places. Think about the buses. Buses usually have a stop in the city and a stop at the bus station. Now, during daytime, they are not allowed to go into the city. So it means that it is somehow capacitated. There is some limitation on the node. Okay, but these are all complications, and we are probably not going to see a lot of those in the problems that we are going to solve. Of course, again, remember, my aim is not to go over the networks and teach you networks. My aim is to make sure that you understand that we have a mathematical representation issue that we can handle with networks. Okay, now the last one is important. In most of the applications that we are going to see in this course, we are going to put some numbers on those arcs. Now, we are going to call it weighted. Arcs will be weighted, meaning that each arc is going to represent something else. And usually, these are going to be numerical values, like it will show the distance, or it will show the time, or it will show some kind of a cost. What's the meaning of that? If I am going from A to B, and if I have an arc that goes in between A and B, let's call that arc AB, okay? If I have a number on that arc, it means that it is the cost of going from A to B, or it is the distance of going from A to B, or it is the time that it takes to go from A to B. It's a numerical value. Actually, that is the performance measure that we are going to have. So we usually put that on the arc. That's the way we represent it. Very similar to maps. If you are familiar with maps, if you're talking about the distance between two cities on a certain road, you have some numbers there in between junctions. They write actually the kilometers to go from one node to the next. But we are usually going to have either cost or time as well as distance on the arcs. Any performance measure. Okay, questions on this? Okay. Now, this is basically the problem that we are going to work on. We are going to solve a shortest path problem. These are the nodes that we have. Note that these are the numbers that I am talking about. Let's say that it's cost without loss of generality. It can be time or something else, but let us say it's cost. If you don't like cost, I can say that it's time. Okay, some people, although they are in the Department of Industrial Engineering, they hate the word cost because they think that we're too ambitious with respect to minimizing costs and killing all the workers. No, it's not going to be like that, of course, but you can call it time or distance or anything else as well as cost. It's not going to change anything. Okay, so this is the structure that we have available, and our objective is to go from A to E. So A is going to be our starting node. So Sözeri Kebap is at A, okay? And E is your dorm. Okay, we ordered, or let's say here. It would be nice if we can order pide for the whole class, okay? And see whether Sözeri would be able to deliver it, okay? Like we want 200 portions of Adana, same time. Anyway. So this is our location. This is Sözeri's location. We want to make sure that Sözeri would be able to deliver with minimum cost, so it can either go from different ways to reach E. Now, can you find the shortest path from A to E? Don't shout, but raise your hand when you are done, and I will ask you. Yes? A to B, A to F, AFD, yes? Then E. And the total will be 13. Anybody who thinks that they can beat this number? Okay, it's correct. Now you can see that this problem is very easy to solve. Then why are we bothering ourselves? We are going to learn an algorithm, a mathematical algorithm, which is going to describe everything step by step to solve this problem. Why do you think we are bothering? Because if you increase the number of nodes and arcs, it will be a serious challenge. Now, I am sure that you're smart enough to write a program, a computer program, which is going to solve this by enumeration. Do you know what enumeration is? Enumeration is simply list all the possible ways to go from A to E. Can I do that? Of course I can do that. For example, the first part is AB. Okay, I can use AB. Then let's say CDE is one possibility. Another possibility is ABFDE. Another possibility is AFBCDGE. I can enumerate all these possibilities. Enumerate, let me write that word. We're going to see that word again actually in tomorrow's lectures. Okay, enumerate. You simply select all of them one by one. Now, what your friend did is basically she enumerated all possibilities in a very quick manner. You can do it actually in a very clear way and found out the way to go there. How can you eliminate, for example, enumerate all the possibilities? You start with a solution and then you start in a systematic way of finding out all possible ways to go there. You have to make sure that you don't miss anything. Now, of course, if I increase the network size by, let's say, 300 nodes, that solution would be difficult. Even for most of you who can say that, well, I will be able to solve it. So some of you are not going to say that because they are aware that it will be difficult. Now, you think that this is a simple problem. Okay, so this is the problem that we want to solve in a more systematic way, regardless the number of nodes. Any questions on this? Any questions on what we're trying to do? Okay. Now, note that all these arcs are two-way arcs. So when you are enumerating the possibilities, you have to make sure that you can go from F to B, as well as from B to F. But one thing that you always keep in mind when you are enumerating, you don't want to go back to the same node. Am I right? It's not going to be good. In other words, AFBF is not going to be a possibility. You, at most, will visit a node once. This is called a property. Okay? A property of the optimal solution that you may want to keep in mind. Okay? So if you don't know anything about the solution, by writing these type of properties, you can actually decrease the possibility set. This is actually what we do for living as academic people. We take a problem which is not previously solved. Okay? We basically find out some structural properties of the problem. By using those properties, we come up with an algorithm that will solve all types of problems regardless of the number of nodes and arcs. Okay? But of course, the number of those type of problems are not infinite. So this is what we do for living, meaning that we do it as research. And we don't teach that in the undergraduate. We teach only the things that are very basic so that you can use them as building blocks. Okay. So this is, I think, the shortest path problem. Any questions on this? Now, we're going to solve this problem in a more systematic way. Okay. Questions? I just want to make sure that you are with me at this point, because basically the next step is going to be more technical, so that we're going to actually, I don't want you to lose the large picture. Okay, questions? Okay, now, a few more words. Performance measure that we can use is distance traveled, cost, time, and performance measure is whatever the number on the arc represents, and what we want is we want to minimize that. Of course, there might be a performance measure where you would like to maximize it. Remember some video games? The more you travel, actually, the more fruit is going to come. So when you eat that fruit, okay, you're going to get some points. And your objective is to maximize your points when you are going from A to E. That might be a possibility as well. Okay? But here, we would like to minimize the total. Now, can we convert a maximization problem to a minimization problem? Can we do that? How can we convert? Let's say that we have two alternatives. One of them is the game where I was talking about. Every time that you pass through an arc, there is certain fruit that you eat. So that's going to be something that you really like to have. So your objective is to maximize the total amount of fruit that you eat from A to E. And another problem is Sözeris problem, where you want to make sure that you reach the dorm as quick as possible. Now, can we convert these two problems for each other? I don't know. Well, I will be able to answer that, but I'm not going to answer. Now, question is, you can see that we have millions of variations that we can create from this simple structure. Even if you have the same structure, you may want to maximize, minimize, depends on your objective. So at this point, I'm assuming that we have a performance measure where we want to minimize the total distance traveled or the total cost spent. So it's not the fruit problem. There is a way to convert that, of course. Okay. Now, what we're going to do is, okay, we're going to solve this problem in a systematic way. And that systematic, a detailed procedure. Algorithm is actually a detailed procedure. We discussed that. I will write a detailed procedure that will solve this problem. And it turns out that if you apply that detailed procedure, you're going to obtain the optimal solution. Now, this is very important because I think you are probably going to hear this in some other courses, but not in a manner where you don't know anything, but you just want to learn a concept. And at that point, you will be learning certain things, and you may always misuse that word. Now, what is the meaning of an optimal solution? An optimal solution is a solution that yields the absolute minimum value of the performance measure considered. So it means that I cannot do better than that. Okay? That's called an optimal solution. Now, never say, as an industrial engineer or a student of industrial engineer, that my solution is better than the optimal solution. Okay? Never say that. Because the meaning of optimal solution is that it's the absolute minimum that you can achieve, if we are talking about the minimization problem. Okay? So never think that you can beat the optimal solution. Now, question here is, when are we going to be sure that the solution that we obtain is an optimal solution? Okay. I think it's okay. Yeah, thank you. Okay, so again, optimal solution is an important concept, optimality. Now, the main problem that we are going to have throughout, not only this course, but throughout your industrial engineering life is that you think that you have a good solution. Okay? Now, smart people always think that they have a good solution. But unless you are sure, you cannot say that it's an optimal solution. And we're going to see, unfortunately, there are only certain problem structures where we know what the optimal solution is. In most of the problems, we are not going to know how we are going to obtain the optimal solution. But that I remain to the other lectures, to the other courses, okay? So this is a very important concept. Now, luckily, the shortest path problem that I am talking about, we are very lucky to know that if we apply the algorithm that I'm going to talk about, it will yield an optimal solution. This is rare. In general, you would not know whether the algorithm that you are going to apply is going to give you the optimal solution. That's the reason why the idea of improvement is very important. Because if you know that it's not necessarily the optimal, it means that you can improve it. Okay? Are you with me? Or I'm going to repeat this probably this week a couple of more times. Okay? This is important. Now, of course, we want to obtain the optimal solution. However, we may not be able to do that because we may not be able to prove that the solution we obtained is optimal. So if we have an algorithm which is proved to give the optimal solution, we're very lucky. Okay? Now, the algorithm that we are going to see today actually yields that solution. It says that it will always obtain one optimal solution. Now, what is the meaning of one optimal solution? It means that you might have some alternatives as well. Okay? So the idea of alternative optimal solution is very important. You might have more than one solution yielding exactly the same performance measure value. Then we call alternative optimal solutions. Okay? Now, again, if we can obtain an algorithm which tells us at the same time that this is the optimal solution, we're very lucky. Now, fortunately, in your undergraduate studies, you are not going to try to prove that an algorithm is optimal unless you have simple structures. Okay? For example, homework problem number 3, you should be able to obtain the absolute minimum, the optimal solution, because the alternatives are very restricted. Okay? So you are expected to do that by your Calculus 1 knowledge. But unfortunately, in most of the problems that we are going to deal, not in this course, but in the department, you are going to be told that this algorithm yields the optimal solution. Okay? But if you go and further study industrial engineering techniques and so on, you may be able to work with those type of things. Okay. Questions? I can see that you are a little bit lost, but I don't think that it is a problem at this point. Okay. Now, a few more things before we take the break, because I want to spend, after the break, use to the solution of the problem. And the algorithm that we are going to talk about is called Dijkstra's algorithm. Dijkstra. Dijkstra is actually a mathematician who died in 2002, if I'm not mistaken. And Oya Hoca, if you are going to take a course from her, is going to tell some anecdotes about him in your future courses. She has a lot of people that knows Dijkstra personally in common. So basically, but Dijkstra is actually, I think he was born in 1930, so he's not that old compared to me, of course. Okay. And I would call him like medium old type. Now, it turns out that the algorithm yields an optimal solution for the shortest paths from a node to all others. So if you apply the algorithm for the previous problem, we are not only going to find the shortest path from A to E, but we will find the shortest path from A to B, A to F, and A to all other nodes. This is an important result for network theory in general, and it is used by other algorithms in more complicated situations as a subproblem. Okay? And you're going to see those actually in 303 probably, mostly, and then in some other courses. Okay, questions? Okay, now here we have the algorithm, and here is going to be the point that I'm going to stop. And we will continue after the break. Questions? I'll see you in 11 minutes. Buyurun.
Fizik laboratuvarıyla alakalı